So we are just going to continue from the point where we have left, and we were talking about generating random variates from empirical distributions. Remember now, if you have lack of data, or if the data itself does not indicate any known probability distribution as a good model for this random realization, in that case, it might be a good idea to use the data itself. And we have thought that we can use the data itself to generate random variates from continuous empirical distributions using the continuous empirical cumulative distribution function. Now, at this point, we will learn how to generate random variates from discrete empirical distribution. So what is an empirical distribution for discrete random variables? It is basically a type of probability mass function, any kind of probability mass function. However, it should not follow a known distribution. For example, this probability mass function here, as you can see in this distribution, the random variable can only take three possible values, -1, 1, and 2, with these probabilities, and this probability mass function does not follow any known discrete probability distribution. So what is the difference between a discrete random variable and a continuous random variable? Let's just remember, a discrete random variable can take a countable number of possible values with specified probability masses. And these probability masses are indicated by the probability mass function here. And we have a discrete random variable in this example, as I have said, which can take three different values with respective probabilities of 0.25, 0.40, and 0.35. It cannot take any other value. It is indicated by the last row here. So this random variable can take three different values with these probabilities. So if somebody asks us to generate random variates from this empirical distribution, how are we going to do that? Actually, we have already practiced this situation in our second module, and we have learned how to generate random variates for the output of a fair die or for the output of a coin flip. These were discrete random variables, basically. So the output of a coin flip, when you consider the head and tail respectively as 0 and 1, it was a Bernoulli random variable, and the output of a fair die was a discrete uniform random variable. Therefore, we have already practiced this. How are we going to do this? Remember, first we need to determine the cumulative distribution function for this probability mass function. A CDF for a discrete random variable, basically the cumulative version of the probabilities given in the probability mass function in the order of the realized values. So we say 0 plus the first probability mass, 0.25, plus the second probability mass, 0.65, and the third probability mass makes it equal to 1. And we say that if this x value is specified as less than -1, then the probability of this random variable to be less than or equal to that value will be 0, because there is not any probability mass accumulated at that point. But if x is specified between the first realized and the second realized values, in that case, the cumulative probability becomes equal to 0.25, because -1 remains on the left-hand side of this x, and it becomes 0.65 for x values between 1 and 2. There are two probability masses on the left-hand side of it. Finally, if you pass through 2, in that case, the cumulative probability will become 1. Now, what is indicated in this cumulative distribution function, or the CDF? There are three real values that this random variable can take, and we observe jumps in this function at point -1. So actually it is a continuous function in general, but at 3 points it is not. And these points are -1, 1, and 2. And we observe a jump from 0 to 0.25 at -1. We observe a jump at 1 from 25 to 65. And we observe a jump at 2 from 65 to 1. So what we are going to do is this. We are going to create three sub-intervals within the unit interval. The first interval will correspond to 0 to 0.25, the second interval from 25 to 65, and the third interval will start at 65 until 1. And we will say that in our random variate generation scheme, again, we are going to use a pseudo-random number. And if the pseudo-random number is within the first interval, then the corresponding random variate will be -1. If the pseudo-random number is in the second interval, which has the length of 0.40, as you can see, then the random variate will be equal to 1. And if our random number is between 0.65 and 1, then our random variate is going to be equal to 2. So basically, our random variates will get these values if the corresponding random number falls in a subinterval at the length of the probability mass that corresponds to only that value. So this is the generation scheme for discrete random variates in general. So from any discrete distribution, binomial random variable or Poisson random variable or Bernoulli random variable, this is the general idea of generating discrete random variates from these distributions, of course, when you know its cumulative distribution function and when you have a pseudo-random number generator.